Welcome to this coding session. Today, we'll be solving LeetCode problem number 1486, titled XOR operation in an array. This problem focuses on bitwise operations and array manipulation, and it's a great opportunity to practice computational thinking and optimizing algorithms. Let's dive in. In this problem, we are tasked with finding the bitwise XOR of elements in an array. The array is defined by two inputs, an integer n, which specifies the number of elements in the array, and an integer start, which serves as the starting point for generating the array. The formula used to construct the array is nums, I equals start plus 2 asterisk I, where I is the index of the array, ranging from 0 to n1. Once the array is created, we need to calculate the XOR of all its elements and return the result. The constraints ensure that n ranges from 1 to 1000 and start ranges from 0 to 10,000. So we need to handle both small and large inputs efficiently. Let's explore this further with some examples. For the first example, we are given n equals 5 and start equals 0. Using the formula nums, I equals start plus 2 asterisk I, we calculate each element of the array. Nums 0 equals 0 plus 2 asterisk 0 equals 0, nums 1 equals 0 plus 2 asterisk 1 equals 2, nums 2 equals 0 plus 2 asterisk 2 equals 4, nums 3 equals 0 plus 2 asterisk 3 equals 6, and nums 4 equals 0 plus 2 asterisk 4 equals 8. This results in the array 0, 2, 4, 6, 8. To find the result, we compute the XOR of all these elements, 0 XOR 2 XOR 4 XOR 6 XOR 8. The XOR operation is performed step by step, and the final result is 8. Therefore, the output for this example is 8. Now, consider the second example where n equals 4 and start equals 3. Using the same formula, we calculate the elements of the array. Nums 0 equals 3 plus 2 asterisk 0 equals 3, nums 1 equals 3 plus 2 asterisk 1 equals 5, nums 2 equals 3 plus 2 asterisk 2 equals 7, and nums 3 equals 3 plus 2 asterisk 3 equals 9. This forms the array 3, 5, 7, 9. To compute the result, we find the XOR of all these elements, 3 XOR 5 XOR 7 XOR 9. After performing the XOR operations, the result is again 8. Hence, the output for this example is 8. In the third example, we are given n equals 1 and start equals 7. Since n is 1, the array contains only one element. Using the formula, we calculate nums 0 equals 7 plus 2 asterisk 0 equals 7. Therefore, the array is 7. The XOR of a single element is the element itself, so the result is 7. This demonstrates how the problem handles the case where there is only one element in the array. The output for this example is 7. Now let's examine some edge cases to better understand the problem. First, when n equals 1 and start equals 0, the array contains only one element, which is 0, and the result is simply 0. For large values of n, such as the maximum value of 1000, the function must handle the computation of XOR for up to 1000 elements efficiently. Similarly, when start is at its maximum value of 10,000, the computation must account for large numbers in the array. Another interesting scenario is when all elements in the array are the same, such as start equals 2 and n equals 3, resulting in 2, 2, 2. In this case, the XOR of identical numbers cancels out, yielding 0. Finally, the behavior of the XOR result may vary depending on whether n is odd or even, as XOR operations are sensitive to the number of elements involved. These considerations highlight the importance of designing an efficient and robust solution. To tackle the problem, we explored several approaches. First, the brute force method involves constructing the entire array nums by iterating from I equals 0 to n1 and using the formula nums, I equals start plus 2 asterisk I. After creating the array, we compute the XOR of all its elements iteratively. While this approach is straightforward, it has a significant drawback. It requires n space to store the array, which is unnecessary since we don't actually need to retain all the intermediate values. This results in a trade-off, as the time complexity is n, but the space complexity also rises to n, making it less efficient. Clearly, there's room for improvement here, especially in reducing space usage. A more efficient method avoids creating the array completely. Instead, we calculate the XOR directly while iterating. Here's how it works. We initialize a variable XOR_result to 0. Then, for each index I from 0 to n1, we compute the current value as start plus 2 asterisk I and immediately update XOR_result by XORing it with the current value. By the end of the loop, XOR_result contains the final result, which we return. This eliminates the need to store the array, reducing the space complexity to O(1), while maintaining the O(n) time complexity. This approach is both simple and optimal, avoiding unnecessary memory usage. Additionally, it builds on the iterative nature of the problem, making it a great fit for the task. Given the options, we chose the optimized XOR approach as our solution. This method strikes the perfect balance between efficiency and simplicity, requiring only O(n) time and O(1) space. It allows us to compute the XOR directly during iteration without constructing the array, effectively solving the problem with minimal overhead. The brute force approach was discarded due to its excessive space usage, which is unnecessary for this problem. Similarly, while mathematical optimization highlights interesting properties of XOR, it is not practical here due to the specific formula involving start and 2 asterisk I. Overall, the optimized XOR method leverages the problem structure and the properties of XOR to deliver the best performance with clean and concise code. To begin, let's understand the problem. We're given two integers, n and start. Using these, we need to generate an array called nums. The elements of this array are defined by the formula nums, I equals start plus 2 asterisk I, where I ranges from 0 to n1. Once we construct this array, our task is to compute the bitwise XOR of all its elements. Mathematically, this can be expressed as result equals nums, 0, XOR nums, 1, XOR. XOR nums, n1. The challenge lies in how we calculate this efficiently, as the array can grow large depending on the values of n in start. Let's explore how we can break this down step by step. First, let's consider a simple brute force approach. The intuition here is to explicitly construct the array and calculate the XOR iteratively. Here's how this works. We initialize a variable result to 0. Then, we loop from I equals 0 to n1, compute nums, I, as start plus 2 asterisk I, and update result with the XOR of this value. While this method is straightforward, it's not efficient. The time complexity is O(n), since we loop through the array, and it also requires O(n) space to store the nums array. To improve, we can focus on optimizing the computation. Instead of constructing the array, we can calculate the XOR directly within the loop using mathematical properties of XOR. This eliminates the need to store the array, saving both time and space. The key to optimizing this algorithm lies in avoiding the explicit construction of the nums array. By leveraging the properties of XOR, we can compute the result on the fly. For instance, XOR is both associative and commutative, meaning the order of operations doesn't matter. Additionally, XORing a number with itself results in 0, and XORing with 0 leaves the number unchanged. These properties simplify our calculations significantly. Instead of iterating over an array, we compute each term start plus 2 asterisk I dynamically during the XOR calculation. This optimization not only reduces space complexity to O(1), as no additional data structures are needed, but also ensures that we focus purely on the arithmetic pattern of the sequence, avoiding redundant computations. Building on this optimization, let's summarize our final algorithm. Since we no longer need the nums array, the space complexity is reduced to O(1), and we maintain a time complexity of O(n) due to the single loop. Here's how the algorithm looks. We initialize result to 0. Then, we loop from I equals 0 to n1. For each iteration, we compute the term start plus 2 asterisk I dynamically and update result with the XOR of this value. After the loop ends, we simply return the value of result. This approach is efficient and avoids unnecessary overhead, making it suitable for large inputs. When implementing the algorithm, it's important to handle edge cases. For example, if n is 0, the array is empty, and the XOR result should be 0. If n is 1, the array contains just one element, so the XOR result is simply the value of start. For large values of n or start, Python's ability to handle arbitrarily large integers ensures that the algorithm works without overflow. Finally, the algorithm also works seamlessly with negative values of start, as the XOR operation is well defined for all integers. Ensuring these edge cases are covered guarantees the robustness of the solution. Let's walk through a couple of examples to solidify our understanding. In the first example, suppose n equals 3 and start equals 5. The array nums would be 5, 7, 9, derived from the formula 5 plus 2 asterisk I for I equals 0, 1, 2. The XOR calculation proceeds as follows: 0 XOR 5 equals 5, then 5 XOR 7 equals 2, and finally 2 XOR 9 equals 11. So, the output is 11. In another example, let's take n equals 4 and start equals 0. The array becomes 0, 2, 4, 6. The XOR calculation starts with 0 XOR 0 equals 0, then 0 XOR 2 equals 2, followed by 2 XOR 4 equals 6, and finally 6 XOR 6 equals 0. Here, the output is 0. These examples demonstrate how the algorithm handles both small and large inputs efficiently. This implementation solves the problem by calculating the XOR of all elements in the dynamically generated array. The XOR operation method takes two arguments, n, the number of elements in the array, and start, the base value for the calculation. First, we initialize a variable result to 0. This variable will store the cumulative XOR result as we iterate through the array. The XOR operation has the property that any number XORed with 0 remains unchanged, making it an ideal starting value. Next, we use a for loop to iterate from 0 to n1. For each iteration, the index I determines the current element of the array using the formula start plus 2 asterisk I. This formula ensures that each subsequent element increases by 2, as described in the problem statement. Within the loop, the XOR operation, == is applied between result and the current element, start plus 2 asterisk I. The result is updated after each iteration to reflect the cumulative XOR of all elements processed so far. Finally, after the loop completes, the method returns the value of result, which contains the XOR of all elements in the array. This approach has a time complexity of O(n), as it iterates through the array once, and a space complexity of O(1), as it uses only a single variable for intermediate calculations. This is the Java implementation of LeetCode problem number 1486, XOR operation in an array. The logic mirrors the Python implementation, where we compute the XOR of all elements in an array generated based on the given formula. Key differences include Java's explicit type declarations and the use of Java's standard class structure. The method iterates through the array indices, calculates each element, and updates the XOR result. To solve the XOR operation in an array problem, we need to construct an array based on the formula start plus 2 asterisk I, where I ranges from 0 to n1, and then compute the XOR of all elements efficiently. For example, if n equals 5 and start equals 0, we begin by initializing result to 0. In the first iteration, where I equals 0, we compute the value as start plus 2 asterisk I, which gives 0 plus 2 asterisk 0 equals 0. We then update the XOR result, result_0 remains 0. In the next iteration, I equals 1, we calculate start plus 2 asterisk I equals 0 plus 2 asterisk 1 equals 2, and update the result to 0_2, which equals 2. For I equals 2, we compute start plus 2 asterisk I equals 0 plus 2 asterisk 2 equals 4, and XOR it with the current result, giving 2_4 equals 6. At I equals 3, the value becomes start plus 2 asterisk I equals 0 plus 2 asterisk 3 equals 6, and XORing this with 6 results in 6_6 equals 0 as identical numbers cancel out. This process continues until all elements are processed. In the final iteration for n equals 5 and start equals 0, or I equals 4, the value is computed as start plus 2 asterisk I equals 0 plus 2 asterisk 4 equals 8. XORing this with the current result of 0 gives 0_8 equals 8. Hence, the XOR of all elements in this array is 8. Now, consider another example with n equals 4 and start equals 3. We initialize result to 0 and proceed. For I equals 0, the value is start plus 2 asterisk I equals 3 plus 2 asterisk 0 equals 3, and updating the result gives 0_3 equals 3. For I equals 1, the value is start plus 2 asterisk I equals 3 plus 2 asterisk 1 equals 5, and XORing this with the current result gives 3_5 equals 6. Next, for I equals 2, the value is start plus 2 asterisk I equals 3 plus 2 asterisk 2 equals 7, and XORing this with 6 results in 6 caret 7 equals 1. Finally, for I equals 3, the value becomes start plus 2 asterisk I equals 3 plus 2 asterisk 3 equals 9, and XORing this with 1 gives 1 caret 9 equals 8. Thus, the XOR of all elements in this case is 8 as well. Now, let's look at an example where n equals 3 and start equals 6. The algorithm begins by initializing result to 0. For I equals 0, the value is start plus 2 asterisk I equals 6 plus 2 asterisk 0 equals 6. XORing this with the initial result gives 0 caret 6 equals 6. For I equals 1, the value becomes start plus 2 asterisk I equals 6 plus 2 asterisk 1 equals 8, and XORing it with 6 gives 6 caret 8 equals 14. For the final iteration, where I equals 2, the value is start plus 2 asterisk I equals 6 plus 2 asterisk 2 equals 10. XORing this with the current result of 14 gives 14 caret 10 equals 4. Therefore, the XOR of all elements in this array is 4. By iterating through the array values and updating the result at each step, we efficiently compute the XOR without ever needing to store the full array in memory. The algorithm works by dynamically computing the array elements using the formula start plus 2 asterisk I. This avoids the need to generate and store the entire array, making the solution space efficient. The XOR operation is then applied iteratively, leveraging the property that identical numbers cancel each other out, x caret x equals 0, and combining distinct numbers preserves their uniqueness. This ensures that the final result is computed correctly without additional data structures. With a time complexity of O(n), due to the single loop iterating over the range, and a space complexity of O(1), this solution is both efficient and elegant. By focusing on the iterative XOR operation and avoiding unnecessary computations, we achieve an optimal solution to the problem. In this problem, we are tasked with computing the XOR of an array defined mathematically as nums, I equals start plus 2 asterisk I, where I ranges from 0 to n1. The core of the algorithm revolves around a single for loop that iterates exactly n times. Let's break this down step by step. First, the loop runs from I equals 0 to I equals n1, resulting in n iterations. Within each iteration, several operations are performed, calculating start plus 2 asterisk I, which involves one addition and one multiplication, and applying the XOR operation result caret equals. Each of these operations has a constant time complexity, or O(1). Since the loop runs n times and each iteration takes O(1) time, we can conclude that the total time complexity of the function is O(n). Now, let's analyze the space complexity of the function. The function receives two scalar inputs, n and start, which together require O(1) space. Additionally, the algorithm uses a scalar variable result to store the cumulative XOR as well as a loop index I, both of which also require O(1) space each. Importantly, the function does not construct any additional data structures like arrays or lists to store intermediate results. This means no extra memory is allocated beyond the constants needed for these scalar variables. As a result, the total space complexity of the function is O(1), highlighting its efficiency in terms of memory usage. To appreciate the optimization in the given solution, let's compare it with a brute force approach. A naive method might involve explicitly constructing the array nums, which requires O(n) time to generate and O(n) space to store. After constructing the array, another O(n) time would be needed to compute the XOR of its elements. Therefore, the brute force approach would have a time complexity of O(n) and a space complexity of O(n). In contrast, the optimized solution avoids constructing the array entirely. Instead, it computes the XOR directly within the loop, which reduces the space complexity from O(n) to O(1), while retaining the O(n) time complexity for the loop iterations. This optimization demonstrates how avoiding unnecessary data structures can lead to significant improvements in memory efficiency. Finally, let's consider the best, average, and worst-case scenarios for this problem. Since the number of iterations in the loop depends solely on the value of n and does not vary based on specific input values, the time complexity remains O(n) across all cases. To validate this further, we can use mathematical reasoning. Each iteration of the loop involves constant time operations such as addition, multiplication, and XOR, all of which are O(1). With n iterations, the total time complexity is therefore O(n*(O1), which simplifies to O(n). On the other hand, the space usage remains constant regardless of the value of n, as no additional memory is allocated beyond the scalar variables. This confirms that the space complexity is O(1), making the solution both time and space efficient. Let's start by addressing some common mistakes that arise when solving this problem. First, it's easy to overlook the correct range for the index I. Since I ranges from 0 to n1, using something like range 1n instead of range 0n will lead to incorrect values for nums I. The fix is simple: always ensure you're using range n to include all indices. Another frequent error involves misunderstanding the properties of the XOR operation. Remember, XOR is not addition x(x) equals 0, and x(0) simply gives x. Additionally, it's associative, meaning the order of operations doesn't matter. If you're not careful with these properties, your solution might produce incorrect results. Finally, a common inefficiency is generating the entire array explicitly, which takes O(n) space. This is unnecessary because you can calculate the XOR directly without storing the array. The key here is to adopt a formula-based approach that works directly with indices. Another mistake developers make is hard-coding edge cases, such as manually handling small values of n or specific start values. This approach doesn't scale and will fail on larger, more complex test cases. Instead, your code should be general enough to handle any valid input dynamically. Additionally, while Python gracefully handles large integers, other languages like Java or C++ may encounter integer overflow during arithmetic operations. This can lead to incorrect results unless you manage data types carefully or apply modular arithmetic. If you're coding in a language with fixed integer sizes, always be mindful of these limitations and test for them. Now, let's focus on how to approach this problem in an interview setting. Understanding bitwise properties is crucial. Since XOR is both associative and commutative, you can reorder or group the operations without altering the outcome. This is a powerful property that can help simplify calculations. Another insight is recognizing that nums I equals start plus 2 asterisk I forms an arithmetic progression. By detecting this pattern, you can often reduce the problem to a mathematical formula. While O(n) brute force solutions may be acceptable for small inputs, interviewers typically expect you to optimize further, aiming for O(1) complexity by leveraging patterns or mathematics. Additionally, it's important to clearly explain how you handle edge cases. For example, when n equals 1, the array has only one element, so the XOR result is simply that value. Similarly, think through scenarios like start equals 0 or even n equals 0 to ensure your solution is robust. Let's now look at some related problems that reinforce the concepts covered here. In LeetCode 136, single number, you use XOR to find the unique element in an array where every other element appears twice. LeetCode 268, missing number, applies XOR to locate the missing number in a sequence. The problem we're discussing, LeetCode 1486, XOR operation in an array, is another great example of how XOR can be used for mathematical simplification. Lastly, LeetCode 260, single number 3, involves finding two unique numbers in an array using XOR. Each of these problems helps deepen your understanding of XOR and its applications in different scenarios. Finally, let's examine alternative approaches to solving this problem. The brute force approach involves generating all nums I values explicitly and then iterating through them to compute the XOR. While straightforward, this method has O(n) time and space complexity, making it inefficient for larger inputs. A better option is the optimized XOR calculation, which uses the arithmetic sequence formula to compute the result directly without generating the array. This approach is highly efficient, with O(1) time and space complexity, though it requires a solid understanding of XOR properties. Another alternative is the recursive approach, where you compute the XOR result through recursion. While this method can be useful for practicing recursive thinking, it may be less intuitive and slightly slower due to the overhead of function calls. Each approach has its trade-offs, so choose the one that best fits the problem's constraints and your learning goals. Great job on completing the problem. To summarize, we explored how to compute the XOR of a dynamically generated array using an efficient approach. This problem highlights the power of bitwise operations and their applications in constructing optimized solutions. Keep practicing, and don't forget to subscribe for more coding content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!